Test. That. Okay, perfect. Great. Well, I think I gave a quick intro to the first meeting, but just to introduce myself since we have so many new people here. My name's Korey. I work at Klarna. Unfortunately, not in AI at the moment. Primarily working on the integrations to different shop systems and payment service providers. But I'm definitely following Square in the volunteering, hoping that from presenting this stuff that we can get like a better understanding together on some of these machine learning concepts. So not necessarily an expert here, but happy to share kind of what I've found so far. And what we're going to talk about as the sort of title of this event is what is a GAN? So if you don't know anything about GANs, you've come to the right place. And hopefully, if you do know a lot about GANs, I can at least show some things that maybe you haven't discovered lately in the past, or some new concepts, because the world of GANs is kind of ever-changing, it seems. So as Anson mentioned, we've already seen this man's face already tonight, but Jan LeCun, he is obviously very super excited about GANs, and I put both these quotes up here because I thought it was funny, because one says, this is the most interesting idea in the last 10 years, and then he was also in quote saying it's the coolest idea in the last 20 years. So obviously this is a very exciting field of machine learning, and Jan is definitely excited for it. So if anything, I guess the main goal for tonight is I want everyone to sort of share in that excitement and be like Jan. So even if you haven't heard anything about GANs before, or if you have already and you've kind of made, maybe it's not an interesting space for you, I hope at least some of the things that I shared to you tonight will get you excited about what GANs can do, because it's a quite interesting field of machine learning. So a little bit about the history of GANs. So this is the GAN father, just to continue more of the gangster references. I don't know if Ian calls himself the GAN father, or if that's something that media has labeled, but a little bit about him. So what really he kind of did from a problem solution perspective was, we had in machine learning generative networks before, where they could generate images, but those images were actually quite crap as far as what you could see or the quality of them. So in a bar, as most great decisions happen, one of his colleagues came and presented him this problem, and then the same night of, and this is obviously the myth or the legend, he went home and coded a way to present having two competing generative networks, and what that actually can yield as far as output in comparison to one generative network, which is one of the big things I think going into this is so special, I think, about GANs in comparison to them other networks. So what really is all of the hype about? Why does everyone kind of excited in the last 5 years, I guess, in machine learning? Really, if you break down the generative, or GAN being a generative network, first and foremost is that if you look at the two sort of distinct or different types of algorithms or networks that we could deal with in machine learning, first we have the discriminative algorithms, which I think most people are sort of used to, or if you see machine learning in the media, that's normally what's happening. So it takes features of a certain data and provides labels to them. So you can think of like an email filter is saying spam or not spam based on the ways the subject matter, the subject title, or what it looks like, or where it's coming from, the recipient. So in mathematical terms, it's given the probability of y, what is x, or the output of x. Where generative algorithms are quite different. It actually takes labels that's provided, and it then provides labels based on the actual features of what it sees in the data. So instead of producing, having data with a bunch of tails, you can say, okay, this is a dog, rather than looking at spam or not spam. So it's saying, given the probability of x, given y. So it's really asking the question of, how do we get to x in a generative algorithm or a generative network? And then the other crucial part of a GAN is the adversarial part. So like I said, the main concept is we had generative networks, and they were working fine, but they just weren't really producing convincing images. Now, if you want to make them produce better images, we present an opponent. So the classic kind of example I saw really about how to explain the adversarial was forging forging currencies or forging artwork. So I kind of just twisted it a little bit just to make it a little special, but it's really the idea of, okay, how do we make something fake and convince another network that it's actually real? And so in this case of scenario, I say, how do we sort of make the best fake ticket? Let's say we're trying to get into a stadium or a concert. We want to not actually pay, but use a generative network to do so. So the two main concepts is that there's a generator network, which is you being the individual that wants to actually make the fake ticket, and then there's a discriminator network, being, in this example, sort of the stadium security or whoever's checking the tickets. So those are the two sort of main concepts of how we take two neural networks and compete making the best, or allowing the generative network to actually fool the discriminator network. So looking more specifically around the generator network, first the input that you're actually presenting the generator network is just actually random noise, which gets represented by Z in most representations or most formulas. The action that actually takes from the generator network is that it's actually, the goal really is to generate as many different images as possible. So it's not actually focusing on producing the perfect image. It's actually just, the output really is focusing on how can I produce the most amount of what I can present to the discriminator to convince it or fool it and learn from that actual feedback loop presenting to the discriminator network. And the goal obviously is then to fool the discriminator, to present the fake ticket and to get into the concert. And that's actually gets presented as D of G of Z. So G being the output of the generator network, and D being the sort of function of the actual discriminator. So the output is turned to 1, then we know that we've sort of hit a real ticket. The discriminator network, it's a little bit different. So its actual main input is training data. So the training data being real tickets or real images. So it knows exactly what that is, which normally gets represented as D of X. And then the action is that now it takes two different data streams. It takes one being the data set that the training set of real tickets or real images, as well as the generator data set, what we're taking in to compare that actual data that it's receiving from the generator. So the goal here is really to labeling the output of the generator to fake. So that's its main reason for being, is to present something 0, so D of G of Z being actually a fake ticket. So this is kind of just a brief overlook of, or outlook of the architecture of being there. So we have the random noise that goes into or being fed to the generator to produce the fake image. And then we have the training data set that we know of real images. Those both go into the discriminator network and then present real or fake based on in its comparison of the two inputs there. And then this is directly from sort of the original paper by Goto, but again, really just sort of explaining the process of taking X with the sample data, using the function of D, and then the discriminator trying to push this to 1, being, or either tries to have it actually 0 because it wants to be a fake, and then going also back to the generator, which is the input of Z, using that function, sampling that from X, and then looking at the answer as D of G being near 0 or D of G being near 1. Yep. How can I help?
So is 0 the fake and 1 the real image? Or is that
Yeah, 0 is fake, and 1 is real.
so the network is trying to push to make it 1?
Yeah, the generator is, yes, and the discriminator is pushing to make it 0. So the idea here, I think, is that the end goal here is one that. As far as the training, is that you either want, obviously, the generator to, or the discriminator to push it to 1, saying it's a real ticket, but when you know that you've kind of hit the sweet spot is when the discriminator is actually returning things like 0.5, or it's a 50-50 shot that the discriminator is saying, I don't know if this is real or fake, so I'm just kind of guessing. through the whole process. And technically, you can also, at that point, remove the discriminator network at all, because there's no function for it to be there if it's not producing anything of value. And then now the generator network can kind of take over, and you can present the noise or to the generator network, and then the output desired being a fake ticket can be produced. So that's kind of ultimately where you want to be at when designing a GAN, or how to actually produce a functioning GAN. And this is also called, sort of in game theory, the Nash equilibrium, which is, I'll go into a little bit more about how to train networks, and this is really, really difficult to get to in most cases. But it's really that, to the point that, you know, the generator is really trying to maximize the final classification error. So that meaning that the discriminator is making errors on actually the call, but on what the output is. But it's actually making the ideal result, which is producing something saying it's a real, even though it's a fake. And then the discriminator is trying to minimize this error. So this in game theory is called a min-max game. So if you do any independent research on this, you will probably see a lot of those references there. And then this is kind of how it's represented in the functions of the discriminator output being the real data, and then the generated fake data that I mentioned, which is G of Z. So some training challenges. So one of the things that, I mean, GANs are quite like new-ish, and it's one of the biggest cons of using GANs for anything is that they're really hard to get that equilibrium, and there's a lot of times if you don't get it, then it's quite useless to use. So one of the issues obviously is that if the discriminator is too easy to fool. So this is a two-headed chipmunk, and it was produced by a GAN that the discriminator, looking at the parameters and looking at this, it was just too easy and thought this was actually a real chipmunk. So, I mean, maybe in some worlds two-headed chipmunks exist, but this is obviously when the discriminator is too easy to fool. And then the other, obviously the flip side is if the discriminator is too hard to fool. So the generator is producing the noise or producing the output, and it's actually not getting the proper feedback or proper any sort of loop around that from the discriminator to know how to actually improve on the images there. So it's actually producing nothing. And then another big one is mode collapse. So these are actually, this example here is two different GANs producing using a data set called MINST, which is like a number data set that's quite popular to use, where it's generating actually the numbers, and you can see kind of going down that this is actually supposed to look 1 through 10. While the other generator, or this GAN below here, you can see is actually producing the same things over and over again. And what happens here is that the generator is generating limited examples, so it finds one kind of optimal point and says, well, I'm satisfied, I can just keep on going with this, because the discriminator has produced this as being real. So what should happen is that the discriminator should actually identify this as what was called a collapse point. So it should detect that this is something that's getting produced over and over again, and actually provide feedback onto the discriminator, or to the generator, that it should now produce something a little bit more or different.
Yeah, so when the generator happens to come to this suboptimal point,
Yeah.
does it, you see, I mean, what I want to ask is, you had this criteria that the generator should be using a value of which was 1 minus real.
Yeah.
Does, when it comes to these suboptimal points, does it add 0 as a result, or is it close?
It's it's actually more close to 1 for this, but the optimal point is not only real, like 1 to real, but also that it should represent the data set that the discriminator is utilizing. So in this case, the discriminator has a data set that actually looks something close to this. So it's in the generator is producing something that's a representation of, or close to what the discriminator data set is. In this particular case, while it's getting a high result, let's say close to 1, it's not actually representing real images. So I'll go a little bit more about different approaches to GANs, but you can say if there's a face, and this is just all like your face, for example. Like we're producing a whole bunch of faces, and it's just your face. It's a face, but it's not what we wanted a group of faces. Yeah, it's actually coming from that things are modal, like they have different variety to them. I think that's where it's derived from, but maybe when you go into the implementation stuff, you can go into a little bit more about that. But yeah, that's kind of where the term comes from. So yeah, like I said, the discriminator should actually now give some feedback to the generator to point to other different data sets or different production or output. But the only kind of way outside of the mode collapse, if you're kind of trapped in that and that doesn't happen, is to actually completely restart the training. Some other ways to get around some of the other things around like the discriminator being too good or the generator not being good enough is a lot of tips around training these networks in alternative fashions so that there is a constant on the discriminator side as far as actually the way that you train them. And then there's a constant on the generator side. So you train the generator once based on the adversary, or the constant adversary being the discriminator, and then you make changes to the discriminator network after you've made those changes. So you kind of alternate so that they can kind of better themselves throughout the process. And then there's also another kind of way to improve this. It's called the Wasserstein GAN, or the WGAN. And I, to be honest, did not have enough time or energy to dedicate to talking about this, and I think it's almost like a topic on itself. But one of the big things that, it's kind of talked about now is that it's improving the stability of GANs so that you don't have things like mode collapse, and you don't have things like the discriminator being too strong. And the way it does it is actually it weights the ranges for actual the gradient updates. So the gradient being where how you sort of improve or change the training of the networks. So there's a range of that so that you don't change it too much or too little to add some instability to either side of the equation, I guess. And then also it uses a thing called a Wasserstein distance, which is a way which is also called an earth mover's distance. And the example is around how to use the least energy to move piles of dirt around. But it's the idea that how do you now make the easiest decisions in the smallest amount of effort, essentially. And then the discriminator in this sense doesn't actually present real or fake, but it actually helps point to the generator in the what is called the Wasserstein distance. So it points the generator to the range of where it can make different enhancements to itself, but it doesn't it doesn't necessarily present the real or fake. So there's a huge paper there that I've linked there, and you can take a look at it in a little bit more detail. But that's another approach or another way that GANs are sort of improving themselves. But I think one of the interesting things around GANs is just the approaches to how to use them in sort of the real world, if you speak. And I think, and what I mean by approach is kind of applications or where we've probably seen GANs in the wild. So the first one is around generation. So this is an image taken from thispersondoesnotexist.com. So this person is completely fake. Doesn't exist, never walked the face of the earth, but I think it's pretty convincing on what that actually looks like. So this is actually using an approach called the style GAN. And the style GAN first came about by kind of evolving what is called a ProGAN. And a ProGAN is short for progressive generative network. So what it does is you can kind of see the GIF, but it takes like a 4x4 image. It presents that to the discriminator. If that's okay or improves, then it goes and it progresses to an 8x8. Then it goes to a 16x16, 32x32, until it can get to a pretty high quality image. And I think that it ends at 1,204. So you can see kind of the progression here and also the training time it takes to get that. So it's quite cool, but if you notice that this is always a woman, or it's always it's evolving into one type of woman throughout each step. So there's a very limitation to the specific features it could change. You can't really change. She can't, like, from in the end have glasses, or she can have freckles. It's still kind of progressing in one direction based on the feedback from the discriminator. So the individuals behind StyleGAN wanted to find a way to be able to not only make one face or one high definition face, but multiple high definition faces. So they use StyleGAN, which is kind of shown here, where you have a source, so kind of the target, the source or the original face based on what the discriminator network has, and then different course styles that can be copied from there. So if you look kind of really closely to the faces, they kind of have similar elements to them, and it's usually using kind of based on ProGAN progressing the face, but then also using different the different approach that StyleGAN uses, which is first, it actually, what they notice is when you present the initial noise into the generator or use the generator, there was some constant values in the face they could actually hold and not change, so that the faces would remain the same on certain levels, but then they would change other parameters within those faces to allow for modifications like the pose, the face, the shape, and things like that. And what it comes down to is what they call adaptive instant normalization. But what essentially it is in a, you can think of a neural network as different layers. There's a style layer in one neural network, and they actually take that style layer of that neural network and present it to sort of what's called a normal layer of the other neural network that the generator is using. So the style is the same, but all of the other sort of hyperparameters change within these faces to make them quite different. And what they also found was, what they do, they change different axes. They can do different hair colors, different faces, and then they also found ways where there were similarities between like woman with glasses to man with glasses, but man with glasses didn't equal woman without glasses. It's kind of a different approach to sort of editing the faces there. The next kind of thing that GANs can do is text to image synthesis. So you can take a text description and actually make an image based on that text description. And that's using a thing called StackGAN. So StackGAN uses first, it actually uses two stages of GANs. First is the first stage, GAN 1, is using a concept called text embedding, which is kind of using, it comes from natural language processing, but it also processes the text where it can actually represent 0 and 1 based on the text that it's using. So color could be, orange could be 0 and yellow could be 1, things like that. And then it actually then uses another GAN. So the first GAN uses the text embedding as well to make a kind of rough image, which you'll see here. So they're not that great, but they kind of look like birds. The bird is black with the green and has a very short beak. And then the second stage of a GAN, so using another GAN, they use first it takes not Z, but the output of the first GAN, as well as the text embedding that was already produced from the GAN 1. So it's kind of clever in that way that you have two GANs working together. One is using kind of the text embedding and producing rough images, and then the stage 2 kind of refines the image and makes it look a little bit better there. Right? Yep. So the first GAN actually works on the text to produce the image. So the discriminator first actually discriminates on the image itself. So it knows if it's real or fake. Then the discriminator discriminates based on the text. So, well, in this case, it would discriminate twice as far as based on, because what happens is the first stage, it's really hard to make. You can make easy to make fake images based on the text. So it first looks at images to make sure if this is a real image of a bird, and then okay, based on that, is it based on actually the text? Is that connecting to the image that the generator made? So that's the first level. Yeah, essentially, because there's two stages of GANs as well. No, the second stage is another GAN, but a GAN takes first the like random noise to make the images, but the second GAN, instead of taking random noise to make the images, it takes the first images that the first GAN made. So then it refines that, and then it presents it to the discriminator to also discriminate on, is this real and is this based on the text? Exactly. No worries. So the last one is source to target, or domain transfer. So what you can see here is that we have like input being a horse, and you want to change the horse into a zebra, or even different styles of doing. So you have an image that's an input, just a random. It could be a random image, and then you put that in actual styles of Monet, Van Gogh, and I have no idea who those other two artists are. So, but I'm sure they're famous. So that's using CycleGAN. So CycleGAN, similar to StyleGAN, when it uses first a easier GAN system, which it was called pix-to-pix. I'm not sure exactly what the GAN was called. I think it's CGAN, where it takes CGAN or pix-to-pix was able to pair one image to, or based on that image, to another image. So the original data set is actually already kind of prepared, and the discriminator is just saying, is this a real or fake image of a shoe? So we have this kind of hand-drawn shoe here, and a real picture of a real shoe, and those are both being generated by a generative network, and the discriminator is just saying, are these real? But since we already know these two are paired, then we say, oh, well, we've transferred a drawn image to a real image. So that had obviously limitations to it, because the data set is already kind of perfectly pre-formatted, so we have an X and Y, and we're just running those images to a generator network to say, discriminator network to say, are these real or fake? So in a real world where we don't have any perfect data and they're unpaired, so on the right-hand side, we needed a way to sort of find out how to make new images that aren't paired but still kind of transfer the style. And they use, this is where CycleGAN comes in, where it actually uses the unpaired data, but first we have G, so this is like your classic discriminator and generator network, but it also uses F, which is actually the inversion of that. So you can think if you want to translate a sentence to French, and then you translate that language back to English, it should be the same, and that's really what the CycleGAN is testing on. So it uses two generators and two discriminators in this case. So G takes real images and then makes a styled photo, which is like a Monet style photo, and then runs that to a discriminator, and the discriminator says, is this a real image or a generated image? And then F takes that same, or the style photo, and runs it by the discriminator network and says, is this a real or generated image? So it's kind of backtracking in reverse, and that's why I call it the cycle or CycleGAN, because it's taking the one production of the generator and then running by the discriminator again to make sure that it's a real or generated photo. So those are kind of three approaches to GANs, and there's a page called GAN Zoo, and there's about like 100+ other approaches to GAN. So if you're really interested in that kind of stuff, I would definitely recommend looking at that. I think doing some initial research in this, it's quite nice to have kind of the research paper as well as a blog or something that kind of can explain if you're not, in academia alongside it. And I think another great blog that uses this is a Medium site called Towards Data Science, which kind of really explained a lot of, with graphs and charts, a lot of how these GANs or different approaches work and produce them there. But that's basically it for me. So if there's any other questions on GANs and how they work.
Any questions?
Yeah.
Maybe a little bit more about the dynamics between the discriminator and the generator. You talked about like discriminator just giving some output, like if it is fake or not.
Yeah.
But like how, like for example, the weights or like the network, the generator network is evolving based on the evolution of the discriminator. Because based on my understanding, like discriminator is also evolving.
Exactly. Yeah, so that's a good point. So both evolve as far as kind of being able to both each of their goals as far as minimizing or maximizing error. So it's just, I guess, as far as the evolution, you're kind of changing different parameters within either of those either of those networks to generate or to produce either of those desired results. So that's in each network, there's different layers that different parameters, and I think you might go into this a little bit as well on the implementation side of things. But yeah, the discriminator based on, and kind of going to the example of the forging, it knows it can pick up, okay, well, I know based on this being fake, I can look at these labels of what the generator has produced and kind of like improve my idea of what fake is, if that makes sense. So the discriminator can pick up on the details knowing that it's fake based on other details and kind of add that to the network of making decisions on what's fake and what's not. I don't have a slide about like the different layers of the networks, but I think that might be another follow-up as well. Yeah. Yeah, I mean, it all comes down to what data set that you pick for training the discriminator. But you would want a data set that you know is perfect. Yeah, there's available data sets already, so you don't have to like do the hard work. But yeah, the data sets already kind of have a pair of text and what the correct image is. And then what happens is then the generator is actually taking what I mentioned was text embedding and kind of processing the language to compare that to the actual image. And the language gets processed where each of these sort of attributes, if you will, like bird, black, green, short beak, are kind of like transformed into zero and one based on the different attributes there, so that you can kind of return to a generator network. I need to make these changes then. But yeah, it's all about kind of making sure your data set is correct, that you have the birds and the right descriptions first. Yeah, I haven't fully read the paper yet. I have a link to here too, so and we can find a way to share it. But yeah. These are like these could all be separate talks in themselves. I just want to give you kind of like a brief of every them as well. Cool. Yeah, thanks.
All right, I'll make this big and slightly bigger, slightly bigger. Is that too big? Is that okay? It's okay. Is it, I don't really need to read the text. Thanks, Korey. So, all right. So what I'll do, I'll just go through a super quick implementation using MNIST. So it won't be anything super fancy, but I really just want you guys to get the idea behind what the networks are doing. Cool? And so I don't know where I got this from, but apparently, according to Jan LeCun, adversarial training is the coolest thing since sliced bread. So I one more. So he really likes adversarial training. All right, cool. So just before I go through this, how many of you have trained a neural network? And okay, how many of you is this the first time you hear about a neural network? First time you hear about GANs? Cool. All right, so someone will take something away from it. Awesome. All right, so like Korey said, this is the super quick, simplest GAN architecture you can probably think of. And it has basically three components. You have the generator network that's generating images, right? And then you have the discriminator network, which is trying to figure out, are these real or not, right? Or do they belong to this category or not? And then you have a data set of real images. And so you're essentially comparing a real image against a fake image. And the idea is you go back and forth training this network, the generator producing better and better images, and the discriminator getting better at discriminating between fake and real images, until hopefully you reach some kind of equilibrium where the discriminator is at 50-50 between rejecting or accepting images generated from the generator network, right? And when you reach that point, it might not be perfect, but at least the network is, I guess, reached its capacity, right? And now, how many of you have seen Jupyter notebooks in the past? So this is a super standard, really easy to use kind of Python interface that you can use from your browser, and you can run just about anything, and it's just pretty handy for these purposes. Okay. So, like I said, we're just looking at MNIST. So MNIST is this data set of handwritten images, handwritten digits. And it's basically the standard data set, at least it was for a long time, for machine learning classification and generation tasks. Okay. So this is super simple, very bare bones. So we're going to use TensorFlow and NumPy. That's basically it. And then some random and plotting functions. Okay. So nothing out of the ordinary, very vanilla stuff, nothing too fancy. So you can just run this and it loads. And then in this here, we're just going to load the MNIST data set, which it comes pre-installed with TensorFlow, so you don't actually have to go and get the data or do anything with it. So you can just go and get it, and that's it. And if you wanted to see how big it is, there you go. It's around 55,000 or so training examples that we're loading here. Okay. And so this is not like, it's not like high definition images. It's very 28 by 28 grayscale. So it's just really simple. That's basically what they look like, right? But for kind of simple demonstration purposes, you really want these things to be as light as possible so you can actually train it and demonstrate it quickly. Cool. All right. So the first thing we need to do is set up a discriminator network. So very simple. You start with some image, which in this case is grayscale. So it's 28 by 28 pixels and just one channel depth because it's just grayscale, right? So if it was color, it would have 3 channels, right? And if it was like anything bigger, like a video, then it would be like, you know, more channels and so on. But it's very simple. Cool. And this is, let me see here. So how many of you heard of convolutions before? Right, so in this case, we're gonna apply a super simple convolution on this image just to make it better. So just convolution 2D, and then we're gonna do average pool. So which means from the convolution, from the output, we're just gonna take the average. You could do other things like max pool or something, but we're just gonna keep it simple and do average pool. Okay. All right, so let's go through that. And the discriminator network is gonna have, I guess, a number of layers within it, and it's gonna pass just from one convolution to the next, so you have your regular network, your convolutions, you have your activation function, ReLU standard, and your pooling layer, okay? So we're gonna do that a few times, all right? So this basically the component of a network is just repeated layers of this. So convolution, activation, pooling, okay? And then in the end, let's see here, you have a final fully connected layer where you're actually asking the network, is this an image or is it real, yes or no, right? So it's just binary. Cool. All right. So we just have as a function. And then the generator network is slightly different, right? So in this case, we're gonna start with noise, right? So we don't have any preconceived idea, notion of what this is. We're just starting with just noise, right? And the idea is that we're gonna perform, so we start with noise, and then we're gonna perform a number of convolutions, or deconvolutions in this case, to actually go back and change the noise in a way so that we can fool the network. Does that make sense? So we're starting from noise, absolutely nothing, or randomness, and then we're gonna fix the noise in a way so that the discriminator begins to actually fail. Okay? So we go through convolution layers. In this case, it's just, I guess, 4 layers, and then a final H convolution. Okay? And so we can actually go through this. Oh, let me see here what happened. Oh, I think I forgot to actually run this. Let's see here. 1 second. I just ran it like 3 seconds ago. So let me go back and see what I did not run. So already access. Okay, so oh yeah, so it should be fine then, because I already run it there. Okay, so that should be there. I think I already run it. Okay, let's restart the kernel. Okay, so I'm just gonna go through it super quickly and. On which one you said? Here we go. I think it might, let's see, it'll take a while. So you should run the next, you should do the next session. So let's see here. Okay. Where are we? Okay, so I think we get it. There we go. Yes. All right, success. Thank you. And then here we go. So it goes through iteration of that, and it's just producing some noise. Okay. All right. All right. Everyone happy with that? Yeah, I'm happy with that. Okay. So then, of course, what you want to do is just actually train the network and go back and forth until the noise begins to look like actually something useful, right? So you have a loss, so the loss is what actually trained in the network. And let me just see here. So this is just the loss of real versus fake, and your final loss is the loss of real plus your loss of it being fake. Cool. And you're using a standard atom optimizer, and you're trying to minimize over that. Okay, cool. So here is the tricky thing. So the more you train this, the better you'll get. And sometimes it's kind of training, even though it's simple images, they can take a while. So here, I'll just run it for 30 times, just for demonstration purposes, and let's see if the noise improved. Well, a little bit. You can see there's sort of something in the middle, right? Okay. And now let's see, just in the interest of time, if I were to run this 300 times. Okay. Yeah, so the thing about it is eventually you'll reach a threshold where it's full in the discriminator and it's not necessarily giving you good images, right? Like that example. And in those cases, training it for longer wouldn't actually improve the network or the result. So you have to do other things like add convolutions, like in cycle GAN or so, the extended network, or they do 2 different discriminators and so on. But yeah, so that's the idea. And there you go. So it's starting to look like something, okay? One running longer because we have some food, but does that give you an idea of how these things work? So it sounds very complicated, but in reality, it's really just 2 networks working sort of cooperatively or competitively to improve noise into something meaningful, okay? All right, questions, comments? All right, cool. So I'll just upload this to the GitHub, so anyone can go and play with it. And like you said, there's the GAN zoo, and there is literally hundreds of different implementations, more complicated things you can do with this stuff. All right, cool. Thank you, and thank you. Okay, cool. All right.